Hello everybody. Now we come to the last lecture, and in my opinion this is one of the most important lectures today. So I hope you can comprehend this one and concentrate with me, because this will help you to interpret your multiple sequence alignment. Interpretation means that you have to make sense of your multiple sequence alignment. This means that you have to extract blocks which is meaningful and see some special positions in your alignment. Of course, interpretation is a little bit of art, so it needs all your information in biology and computer science to try to interpret your multiple sequence alignment in the right way. Of course, I will not talk much about the e-value score, which tells you how you can rely on your result in your database search. And of course, e-value is very important, and I think in the last module we already described what e-value means. So this, as we said, that means that you decide whether your alignment is correct or not. This needs a lot of educated guesswork. So not just a guesswork, but educated guesswork. So DNA alignment by far is the most difficult to interpret. So because it's only 4 letters, and it's by far this is the most difficult. A high level of conservation is needed, and try to single conserved columns are likely to be meaningless. So don't look only to a single conserved columns, but always take a look at the block of conserved columns. This means something. So that's why a DNA block is only informative when several identical columns in a cluster can be seen. But if 1 or 2 or 3 it doesn't mean anything. Even with DNA of closely-related sequences. So, of course, that's why we always prefer to have to take a look at the protein multiple sequence alignment, because even with a small number of conserved columns, it means something. So how to convince yourself and convince other people that this is giving this few conserved columns give you a meaningful signature or something. You have in this regard, you have to know the difference between primary structure, and you have to know what the amino acid involved in this changing from primary structure to secondary structure and tertiary structure and quaternary structure. So understanding the difference between this protein structure and what are the amino acids that involve in changing from one to another structure, this will help you to understand how important these conserved columns are. So, for example, when you take a look at when you take a look at the structure, you know, of course, that surface loops evolve rapidly. So that's why you will see that these loops in the protein, loops, by the way, are the softer portion of the protein. This softer portion, always you can see that the amino acid in these loops are changing. And there is you can find a lot of mutation in this in these loops. But other places like the rigid portion of the protein, this always you cannot find it change rapidly. So you cannot find a lot of mutation in this part. So usually the rigid part is mostly conserved, but the loops is not very conserved. So. And of course, the core region work as a support walls, so it's evolved less rapidly, but the loops can evolve rapidly, so you can see a lot of mutation in the loops. So anyway, you can expect, if you see gap-free blocks, that this is can correspond to a core regions, but the gap-rich regions can correspond to the loops. This is an example. Number 2 is you have to know the meaning of the capitalistic signs, because you can see a lot of many programs use this, like TCAFE, Muscle, Crystal W, use this sign. So you have to understand what the meaning of these signs. This capitalistic signs, the first one is a star, which indicates entirely conserved column. The column which is entirely conserved, this represented by star. A column indicates columns where all the residue have roughly the same size and hydropathy. So if you have a column that all the residue, maybe they are different but have the same size and hydropathy, so this column can be represented by colon. A period indicate column where the size or the hydropathy have been preserved in the course of evolution. So if the column represented by a period, this means that this column have residues that either have one hydropathy or size. So the average good block, if you look at the multiple sequence element, and you can see a good block, a unit of 10 to 30 amino acid. If you exhibiting, if you take a look and you see that there is at least there is 1 to 3 stars, few more colons, and several periods. This is a very good block. If you take a look at something like this, and you can see that this is a good block to interpret and take a look and maybe give you indication of something. The magic thing about multiple sequence alignment, as we always say, that in protein, if you have at least 10% identity, less than 10% identity, can give you a signal that there is something meaningful. So, for example, if you see 4 to 5 amino acid over 50 amino acid that is conserved and have conserved position, so this means that this may be a genuine signal. But remember that this only when we talk about multiple sequence alignment. But in the last module, as you know, when we use pairwise alignment or on a sequence alignment, at least for protein to have require 25% identity to consider a pairwise alignment. So pairwise alignment or sequence alignment is different from the multiple sequence. Multiple sequence alignment, 10% is okay. Conserved columns in a multiple sequence alignment is meaningful only when surrounded by not conserved regions. This is also very important. So this means that you have to see something signal that is genuine and interesting. So you have to see something, some conserved columns, and this is surrounded by columns that are not conserved. Another criterion for a useful multiple sequence alignment is knowing the type of amino acid you can expect to see conserved. And this we will take a look at some example in the coming few slides. Also, it's very important to know that amino acids are not equal, and they have very characteristic pattern of mutation and conservation in multiple sequence alignment. And we will take a look at pattern of conservation and multiple sequence alignment in the coming few slides. For example, if we take a look at tryptophan, phenylalanine, and tyrosine, if we see this 3 of them, we know that these 3 amino acids are usually set deep in the core protein. So it is important for the rule of their stability, and of course they are difficult to mutate. So this 3 amino acid is usually we can find them in the active sites or something in the protein. When tryptophan, even when tryptophan is mutated, it's replaced by aromatic amino acids such as phenylalanine or tyrosine. So this could be expected. So that's why pattern of conserved amino acids constitute the most of the common signatures for recognizing protein domains. So if you see this 3, you can these 3 amino acids, you can think that this is giving genuine signals for a core of the protein. Glycine and proline is common to find columns of glycine and proline in the multiple sequence alignment, and they usually are in extremities in the beta strand or alpha helix. You can find them easily in the extremities. So that's why if you take a look at your multiple sequence alignment and find these 2, you can guess that this could be at the extremities of the beta strand or alpha helix. Glycine, cysteine, of course, cysteine is of course the disulfide bridge will contain columns of cysteine. So conserved columns of cysteine are common and indicate this such bridge. And of course, columns conserved cysteine with specific distance provide a useful signature for recognizing domain and fold. Also, histidine and serine. Histidine and serine are often involved in catalytic sites, so especially of those of proteases. So conserved histidine or conserved serine are a good candidate for being part of the active site. So that's why take a look and keep your eye open for these two amino acid to understand if there is a really active site there or not. Lysine, arginine, and aspartic acid are glutamic acid. These, of course, as we all know that they are charged amino acids, are often involved in the ligand binding, and highly conserved columns can indicate, of course, salt bridge inside the core of the protein. Like leucine are rarely very conserved unless they are involved in protein-protein interaction, such as, of course, leucine zipper. So that's why if you see columns of leucine, you can guess that they may be a leucine zipper. So and this leucine zipper can help in protein-protein interaction. So I hope you enjoyed this lecture and all the last few lectures today, and I hope that you will enjoy the coming session, which will be on gel view. And you will, in the gel view session, you will take a look at a very good program to use that include many of the program that you use today. So you will enjoy it, because actually it help you. It's one place and one shop that you can buy anything you want from the same shop. So until then, have a good time and try to practice in your own time these practicals, and see you in the coming session, and have a nice day to all of you.